Embed has never been so exciting. It's life-saving. It's life-changing. It's dream-making. And it all starts with this chip. A small and mighty computer the size of a credit card, with embedded chips and processors, enabling our passion and curiosity to solve anticipation of a problem, mitigate risks, and create solutions that improve business and life. The potential that lies behind executing dreams is so tremendous. If we fail to realize them, the responsibility lies solely on us. So dream away. Be great. Enclustra. Embed with us.
Introducing the ultra-compact RFSoC module for software-defined radio applications. Imagine a breakthrough that brings unparalleled speed and precision to the most challenging RF applications. Presenting to you the Andromeda XRU50. This innovation offers an impressive array of features, from a remarkable number of built-in digital-to-analog and analog-to-digital converters to minimal crosstalk between RF channels. Comes in the smallest form factor on the market. Powered by AMD Zynq UltraScale Plus RFSoC, this module offers 8 digital-to-analog converters and 8 analog-to-digital converters for direct RF signal sampling and synthesis, with blazing fast CPUs up to 1.3 GHz. Engineered to meet the demands of 5G networking, phased array radar, and satellite communication applications. You can find it in 2 variants. Choose your perfect configuration with our Early Access Program Development Kit. Get started now.
Welcome everybody to another edition to Enclustra webinar series. Our presenter for today's webinar, Dr. Harry Commin, will walk us through an exciting advancement in RF signal processing, doubling RFSoC ADC rate from 5 gigasamples per second to 10 gigasamples per second. About Dr. Harry Commin, he studied electronic engineering at Imperial College London, receiving a master's degree in 2009 and a PhD in 2013. He then spent 5 years working as a consultant, primarily for the UK government, specializing in algorithm development and FPGA implementation of DSP and digital communication systems. Following that, he joined Ericsson at Stockholm, Sweden, where he implemented high-rate DSP for digital radio ASICs used in 5G base stations. He has been with us at Enclustra in Zurich, Switzerland since 2019 as a lead engineer. Welcome to the studio once again, Dr. Harry Commin.
Thanks, Monica, and welcome everyone to today's presentation, which is all about using digital signal processing to increase the sample rate that we can achieve in a high-performance device like an AMD RFSoC. And specifically in today's presentation, I'd like to try and answer a seemingly simple question, which is, can we somehow create a very high-rate digital signal by combining together multiple slower signals? So, for example, if the ADCs in our system are each capable of sampling up to a maximum of 5 gigasamples per second, then can we somehow combine several of them to produce a single digital output at 10 gigasamples per second? So the presentation will be in 3 parts. First of all, we'll take a look at the ADCs inside RFSoCs, so we can make sure we understand how they are already able to sample very, very fast. Then I'll show you a wideband demo system that we developed last year, and that system already allowed us to exceed the sample rate of a single ADC. But as we'll see later, that system did have one quite significant limitation. And so that brings us to the main topic of today's presentation, which is a technique called frequency interleaving, which allowed us to solve that limitation of last year's system. So first, let's take a look at the hardware platform that we used for doing this work. So this is an Enclustra RFSoC module, and it's carrying a relatively large 3rd generation RFSoC device. So inside that RFSoC, there's some 4,000 DSP slices, about 400,000 lookup tables. And on the module itself is all our DDR RAM and power supplies and so on. But really for today's presentation, the main focus here is that inside that RFSoC are some very fast ADCs and DACs that are capable of sampling at many gigasamples per second. So how are those ADCs inside the RFSoC able to sample so fast? Well, the answer is that they use a clever trick, because in fact, inside each one of those RF ADCs is actually multiple slower ADCs that are being time interleaved together to produce that faster digital output. So in this example here, we're looking at a time interleaved ADC with 3 sub-ADCs. And so what that means is that each one of those sub-ADCs only needs to sample at 1/3 of the output rate, but each one samples at a different time offset. So we can see there, if we combine those 3 sub-ADC outputs together, that will give us that much faster digital output. And in fact, in RFSoC, the parallelization factor is typically a factor of 8 or sometimes 4, depending on the type of ADC tile that you're using. In the device that we use, they were actually all a factor of 8. And so that means that we sample each one of those sub-ADCs up to 625 megahertz, and then they all combine together to produce that very fast output up to 5 gigasamples per second. And then that big block there is just one of the RF ADCs inside our RFSoC, and across the device there are 8 of those in total. So in total we have 64 sub-ADCs in the device, so clearly a very large amount of sampling capability. So really the topic of today's presentation is to answer the question, can we now combine several of those RF ADCs to push the sample rate even higher and above 5 gigasamples per second? So I think the first idea that many of us would have here is, can we just do more time interleaving? Can we apply the same concept as before, but now between several of those RF ADCs? And in theory, that is a perfectly valid idea, but unfortunately, in practice, this is just not feasible. And the main reason for that is that it would require incredibly precise timing precision to be maintained between those RF ADCs in order to make this time interleaving work. And we're really talking about sort of picosecond type timing precision here. And so we just really cannot even get close to that in normal FPGA fabric. So unfortunately, time interleaving is not going to solve this problem for us. So if time interleaving isn't going to work, then what other ideas could we try? Well, I think the first thing we can do here is to move away from thinking about this problem in the time domain and instead start to think about it in the frequency domain, because we've really reached the limits of that time domain idea. So what does our ADC look like from a frequency domain perspective? Well, here we're just imagining our ADC is sampling the unfiltered analog environment around it. So that analog environment has an infinite frequency span. And then a fact that many of us will be familiar with is if we then sample that analog environment at 5 gigasamples per second, then the Nyquist-Shannon sampling theorem tells us that we will be able to capture the information from a bandwidth of half of that number, so from 0 to 2.5 gigahertz. What that theorem doesn't directly tell us, though, is what happens to all of those higher frequencies above 2.5 gigahertz. So we just need to generalize this diagram a little bit. And in fact, what we find is that that infinite frequency spectrum is actually conceptually divided into these zones that we call Nyquist zones. each Nyquist zone has a width of 2.5 gigahertz, and they stretch all the way out to infinity. And so in fact, what we see at the output of our ADC is actually a superposition of all of those infinitely many Nyquist zones aliased down into the same baseband and added on top of each other. And in practice, that's a really big problem because, of course, if we're trying to actually measure or capture some specific signal there, then we're probably going to fail because that signal is just going to be destroyed by all of the interference and noise that is aliasing in from all of those other Nyquist zones. So in practice, what we do is we drop in this analog anti-aliasing filter. And what that filter does is it places a pass band over the one Nyquist zone that we are interested in and a stop band over all of the other Nyquist zones that we don't want to alias in. And so now what we see at the output of our ADC is just the clean information from that one Nyquist zone that we are interested in. But the really key point here is that we don't have to choose the first Nyquist zone. We could, for example, place a band pass anti-aliasing filter over the second Nyquist zone, and then all of the same principles still apply. That will then alias down into the baseband, and so now at the output of our ADC, we only see clean information from the second Nyquist zone. So have we already solved our problem? Because we're saying we could use one ADC to capture the first Nyquist zone, then in parallel, we could use a second ADC to capture the second Nyquist zone, and we could do some kind of signal processing to put those two signals together, and we would double our bandwidth, right? Well, unfortunately, our lives are not quite that simple. And the big problem here is those anti-aliasing filters, because it turns out that any practical anti-aliasing filter must destroy part of the Nyquist zone that we are interested in order to completely remove all of those other Nyquist zones that we don't want to be aliasing in. And so part of this picture here is actually not a practical problem. So losing some bandwidth at those high frequencies up near 5 gigahertz is actually completely acceptable, because in any ADC application, we always accept that we will lose some bandwidth near the Nyquist frequency for filter roll-off. And so in general, we can just design around that and only plan to use the lower frequencies. But the really big problem here is that lost bandwidth right in the center of our frequency spectrum. That is not something we can generally design around. This is really valuable, important bandwidth that we are losing here. And to be clear, we're not only talking about a small amount of bandwidth. In fact, with practical filter choices, we are talking about losing around about 1 gigahertz of important bandwidth in the middle of our spectrum. So clearly that's a really big problem, because it means that if there is some signal in our environment anywhere near 2.5 gigahertz, then we simply cannot capture it. We can't measure it. We don't even know if it exists or not. So clearly, we would very much like to find a solution to this problem if we possibly can. But in fact, we arrived at this stage last year, and we could see that this wasn't going to be a really easy problem to solve, and it was going to need some more investigation. So we decided we wanted to move forwards anyway. We wanted to develop a demo system to demonstrate the wideband processing capabilities of our hardware platform. So we decided we will accept for now that there is this information missing in the center of our spectrum, but we'll proceed to build a demo system with that limitation. So that's what we did. We built a wideband spectrum monitoring demo system. And so the receiver system that you can see in the top of that photo there is basically everything that I've already talked about. So that is capturing 2 Nyquist zones in parallel. It's then computing the frequency spectrum of that signal, which is being displayed on that screen at the top there. And one of our key objectives with this demo system was to try to push the hardware really to its limits. We wanted to see this RFSoC performing under very heavy computational load. And so to do that, we had it computing a very large frequency spectrum of 256K points. And that was really updating continuously and in real time. And so that was updating at a rate of about 34,000 frames per second. And just to give some idea of the size of that spectrum, we would have needed 137 full HD screens stacked horizontally to display all of those data points, just to have enough horizontal pixels to show one spectrum. But then, of course, on top of that, there's also the time axis here, because our screen could only update at 60 frames per second. If we really wanted to display all of that spectrum data that was being output by the device at 34,000 frames per second, then we would also have needed to stack our screens up by a factor of 572. And so in total, we would have needed about 78,000 full HD screens to display all of the spectrum data that the device was calculating. So then on the transmit side at the bottom of the picture there, we can see that we can configure up to 8 independent transmit signals where the user can vary the bandwidth and the center frequency and the power level of each one of those signals. And to do that, they have this video game controller that you can see in the bottom left of the photo, so they could sort of steer the signals around and change their shape and so on. And then, of course, they could look up at the received spectrum at the top, and they could see the corresponding changes happening on the receive side. But I think technically the most interesting part of that transmission system was that it needed to support very, very large interpolation factors. And the reason for that was that we wanted to be able to test from the very narrow band resolution capabilities of the receiver all the way up to its wideband capabilities. So that transmitter was generating RF signals with bandwidths ranging from about 9 kilohertz up to about 600 megahertz. And so to achieve that, we needed to support variable interpolation factors up to more than 1 million. And so there's some quite interesting signal processing happening in that transmitter to achieve those factors. Now, there is a YouTube video where I talk about that demo a bit more. So if you want to see it running, then you can follow this link here. So like I said, we deliberately wanted to really push the hardware platform to its limits with this demo. And so naturally, we ran into various challenges and limitations along the way. And there are really too many of those for me to go into detail today. So I just wanted to highlight what I think was the biggest and probably the most surprising lesson that we learned during this project, which was that we hit the power limit of that RFSoC device much more easily than we were expecting. So the key number here is that the main power supply on the RFSoC device could draw a maximum current of 50 amps, but we found that even with quite an empty design, we were far exceeding that power limit. So to be clear what I mean here, we could actually fit the entire transmit design and the entire receive design quite comfortably into one RFSoC device. And you can see the resource utilization on the right-hand side of the slide there. These numbers are generally quite low. Lookup tables are below 50%, and really none of those numbers are worrying in general, but we still could not deploy that design in one device because of this power delivery problem. And so if I go back to the previous slide, you can see here in the middle of the photo that we actually had 2 complete RFSoC platforms. But really the only reason for that was this power delivery problem. So we had to split the design into 2 RFSoCs, and then each one was drawing approximately 35 amps. And so that allowed us to move forwards. Of course, this is quite disappointing because we buy this nice large RFSoC with lots of exciting FPGA resources in it that we want to use. But we found, at least in this specific case, that we were barely able to use about half of the device before hitting this power limit. But of course, that's an important lesson for us to learn, because now we know, as we're starting our new RFSoC projects, we don't only look at the datasheet values of the resources that are available in the device, we also think very carefully about the power requirement of our processing. Okay, so despite running into some challenges and deliberately hitting the limits of the device with that project, we were generally satisfied with the results. We put that demo together very quickly, it worked, and we felt that it demonstrated the wideband processing capabilities of our hardware platform pretty well. And so overall, we felt that that had been a success. However, we still had this annoying feeling because we had not solved this problem of that missing bandwidth in the center of our spectrum. And so at the end of last year, we decided to return to this problem and find a solution. And actually, this project turned into the master's thesis of my colleague, Timon Kaufmann at ETH Zurich. The title of his thesis is there. It should be available for download publicly now. If you can't find it, then please just drop me an email and I will gladly share the PDF with you. But just to be clear, the work that I talk about now is all Timon's work from his master's project. So how could we try to solve this problem of this missing information in the center of our spectrum? This is really quite a fundamental problem because you fundamentally cannot capture information near the Nyquist frequency. That is unfortunately just how aliasing works, and it's just a limitation of practical filtering. So we searched through the academic literature and we did find some papers where people had solved similar problems using external analog components, especially using analog mixers and some special analog filtering. But we're FPGA engineers. I am primarily a digital engineer, so I really wanted to find a purely digital solution to this problem. And so that's what we did. And I think the solution we found was really quite a simple idea, which was, if we fundamentally cannot capture information near the Nyquist frequency, then why don't we just move the Nyquist frequency? And what I mean by that is that we can now add a third ADC that is sampling at a different rate from 5 gigasamples per second. So for example, if it samples at 3 1/3 gigasamples per second, then now what we find is the Nyquist zones are aligned differently. And in particular, this second Nyquist zone is now centered perfectly on that 2.5 gigahertz frequency gap that we are trying to fill in. And the good news here is that the clean usable bandwidth in that new ADC channel is about 1.33 gigahertz wide. So that's more than enough to fill in that 1 gigahertz gap that we are trying to fill. So this is great news here, because what these diagrams are showing us is that now all of the information can enter inside the FPGA. And once it's in the FPGA, we can do digital signal processing. And so we can start to become quite confident now that we are going to solve this problem. Of course, there are still some practical challenges that we need to overcome here. For example, how do you even combine 3 different signals together to produce one consistent, coherent, and distortionless digital signal? And I think the key word there is distortionless, because more formally what that means is that the frequency responses of all of those anti-aliasing filters must actually add to exactly 1 across the entire frequency spectrum, because if they add to anything else, then that by definition would be a distortion. And to be clear, when I say they must add to 1, they must add to the complex number 1, because these filter responses are complex valued. It is not enough to just ensure that their magnitude responses add to 1. We must also ensure that their phases are going to combine coherently, because if you add 2 signals in antiphase, then they will just destroy each other, which would be a huge distortion. So in theory, what that means here is that we need to have 0 phase across that entire frequency response. Or more practically, actually, all we need is linear phase, because that is basically the same as 0 phase, except that we allow some delay from the input of our processing to the output. But apart from that delay, 0 phase. So can we even make filters that have this property? This seems like a very special requirement, that these anti-aliasing filters need to somehow add up to exactly 1 across all frequencies with some very special symmetry in their overlaps that are going to make that possible. Is this even physically possible? Well, luckily the answer here is yes, this is physically possible, because it turns out that all Nyquist filters have exactly this special property that we need for this application. And this is really a piece of good luck, because if you've heard of Nyquist filters before, it's probably because of a time domain property that they have, which is very important for digital communications. But it turns out that by definition, all of those filters have exactly this special frequency domain property that we need here. So that's some good news, because it means we know these filters exist and we know how to make them. So the most famous type of Nyquist filter is called a raised cosine filter, and that just means that these transition band shapes have cosine shapes. So we call those raised cosine filters. And raised cosine filters are extremely widely used, so they're really well studied, they're well understood, and we even know how to parameterize them so that we can adjust those pass bandwidths and transition bandwidths so we can really fine-tune them for our specific application. So this is great news because this now gives us the perfect framework to start building those frequency responses we need to do our frequency interleaving. But before we rush too far ahead of ourselves, let's not forget that until now, we were really talking about these anti-aliasing filters as being analog filters. And we certainly cannot create nice, clean, ideal-looking raised cosine filters using analog components. And in practice, we'll find that our analog filter responses will look much more distorted, like the ones on this slide. And these are the real filters that we actually used in this work. And so clearly those are more distorted and don't look like nice, clean raised cosine shapes. But luckily, this is a problem that we face very often in digital signal processing. So there is a well-accepted solution, which is to apply digital equalization. So that means that we apply a digital filter inside the FPGA that corrects that ugly, distorted analog filter response and converts it to this nice, clean, raised cosine shape that we are looking for. And again, remember, we are not only equalizing the magnitude responses here, we are also linearizing their phases so that these signals will add together to give that distortionless output. And just a nice detail here is that we were able to independently optimize those two filter overlap regions. And that was very important in our work because we actually had some difficulty finding analog filters that perfectly matched the frequency bands that we were targeting. And in particular, that center filter was a little bit offset from where we really wanted it to be, but we were able to compensate that by adjusting the digital filter roll-offs. And that just allowed us to minimize the distortion in our final output. But really, this completes our concept because now we have everything we need. We have our 3 ADC channels. We have equalized them to give us that nice raised cosine shape. And so now all we do is add those 3 signals together, and that will give us our 10 gigasamples per second output. So now we're ready to start drawing this idea as a block diagram. So we can start with what we had last year, which was just 2 ADCs, each sampling at 5 gigasamples per second, and each one is targeting a different Nyquist zone. And so now what we're saying is we need to add some digital equalization to the outputs of each of those ADCs, and we need a bit of upsampling to get us from the ADC rate of 5 gigasamples per second to the final output rate of 10 gigasamples per second. And then finally, we're adding in this third ADC channel, which is going to fill in that gap in the center of the spectrum. So this is the ADC sampling at 3 1/3 gigasamples per second, targeting its second Nyquist zone. And again, we have some digital equalization that's going to give the raised cosine shape that we need. And then all we do is add those 3 signals together, and that gives us the high rate output we're looking for. Just a practical note here is that all of these filters are implemented using a polyphase structure. That doesn't change anything conceptually or even numerically about this. It's just an optimization that allows us to use fewer FPGA resources to achieve the same result. So now that we have an architecture for our frequency interleaved ADC, naturally the first thing we did was we simulated this idea in MATLAB just to make sure that the concept generally makes sense. And yes, our simulations confirmed that. So this graph here is just showing the output distortion as a function of the input frequency to our frequency interleaved ADC. And basically the graph is showing we have very low distortion across all frequencies. And largely that distortion is below -60 decibels, but in a couple of places it does touch slightly above -60, but we were able to find that that was caused directly by the analog filters that we were modeling in this system. So in particular, that yellow filter response there on the right that's covering the high frequencies, you can see has some quite large side lobes at the lower frequencies, and they map directly to that higher distortion that we're seeing in our output. So of course, we could have selected some higher quality analog filters, and that would have pushed down this distortion a bit lower. But really, there was no need to do that because the key result here is that we are not observing distortion from our digital concept. We're really just seeing the fundamental limit of the external analog system that we were modeling. So this is certainly good enough for us to keep moving forwards. So if we want to move forwards now from a conceptual simulation towards a real digital system running in real time, then we need to think a bit more about the digital performance aspects of that system. So the digital part of this system is really just those equalizing filters. And those filters themselves are really just FIR filters. So we need to answer the normal questions we have when we design any FIR filter. So that's questions like how many coefficients should each of those filters have, and what should the values of those coefficients be. So in terms of the number of coefficients, this is really a pure trade-off between performance and resources, because if we increase the number of coefficients in our filter, then that will improve the performance of the equalization, it will decrease the distortion in our output, but in order to do that, will require more computation, and so we will need to invest more FPGA resources to get that better performance. In terms of the coefficient values, there are really many different ways that we could calculate the equalizer coefficients in a system like this, but I would say the one key ingredient that all of the good practical techniques must have is that they must rely on calibration. And the reason for that is that all of these analog filters, and in fact the whole analog front end, will tend to have some variability as a function of component tolerances and temperature and so on. And so if we want these equalizers to work really well, then they cannot just rely on datasheet values for those analog components. We really need to measure the true distortion through that analog front end by injecting a known calibration signal and measuring the distortion. So the key is calibration, which means we need some kind of hardware setup to allow us to inject those calibration signals into the receiver. Now, ideally to do this, we would use some kind of very high quality calibrated RF signal generator. But usually that type of equipment tends to be somewhat expensive. And also in my experience, it's usually in very high demand. And so it's difficult to get your hands on it. So we decided for this master's project, we would just keep our life simple by generating that calibration signal using the RFSoC itself. And so we would just loop it back out of the DAC and back in to its own ADC. Now, this is certainly not an ideal calibration setup, first and foremost, because that DAC is not calibrated. And so that puts some extra stress on the equalizers in our receiver, because of course now we're not only equalizing the distortion from the receive path, we are also having to equalize any distortion coming through the transmit path. And a second consequence of that is that, of course, we can then only deploy this design in this specific loopback configuration, because we are only calibrating it for this specific signal path. We can then only use it in this configuration. But really, for the sake of this master's project, we were perfectly happy with these limitations. They didn't change our concept at all, but they did make our lives much simpler by simplifying our calibration setup. Another limitation that this setup gave us was that it meant we could not quite achieve 10 gigasamples per second. And the reason for that was that the DAC in our device had a maximum rate of 9.85 gigasamples per second. And in fact, because of the reference clock that we were using, we actually rounded down to 9.6 gigasamples per second. But again, we really were perfectly happy with that. This changes absolutely nothing about our concept. It's just a small numerical difference. So then, of course, the idea is we transmit our calibration signal out of the DAC, loop it back into the ADC, then we capture all of that received data into the DDR-RAM, and then from DDR-RAM, we can offload it into software like MATLAB, where we can then calculate our equalizer coefficients. Like I already said, there are many different ways that we could have calculated those equalizer coefficients. We just went for probably the simplest method, which was just an ordinary least squares calculation. The core part of that calculation is just this one line of MATLAB code here. I won't go into the details now. If you're interested, then all the details are in the master's thesis. So one detail that I haven't touched on yet is what actually were these calibration signals that we were generating and transmitting out of the RFSoC. Again, there are several different options we could have chose here, but I think the one key ingredient that calibration signal really needed was that it had to be very wideband. And the reason for that is that we need to calibrate our receiver across the entire frequency range. So that means we must transmit calibration energy across that whole spectrum. And so, for example, we could have used some kind of wideband pseudo-noise type signal that could have worked very well. But again, we went for probably the simplest and most robust option, which was just a linear chirp signal. So that's just a sinusoidal signal whose frequency varies linearly as a function of time. And historically, linear chirps have been very popular because they tend to be very easy to generate in digital hardware. However, as I've spoken about a few times in the past, it turns out that many of the things that we've been doing for some decades quite easily in digital signal processing turn out to be somewhat more difficult to do when you need to do them at extremely high rates and in parallel. So I won't go into the details here, but I just wanted to give a quick taste here of the extra complexity needed to perform this chirp generation in parallel. So on the right here, I'm just showing one part of one subblock of this signal generation. And you can see there's a little bit of tricky arithmetic that we need to do to calculate the phases of this chirp correctly in parallel and in real time. But to be clear, in terms of FPGA resources, this is really negligible. It's a small amount of logic. It was just more from a conceptual pen and paper point of view. It did take some effort to figure out what we needed to do here. But anyway, we figured that out. We implemented this in VHDL, we verified it, and then we deployed it into the RFSoC device, and then that allowed us to calibrate our receiver equalizers. So then, with our nicely calibrated system, we were able to start running some real hardware tests. So here I'm showing some data captures from a hardware test. One of the nice things about using linear chirps for these hardware tests is that we can effectively see the frequency domain response in these time domain signals. So you can see here that the x-axis is labeled with frequency going from 0 to 4.8 gigahertz. Then I think the first thing that's interesting to note here is that on the left-hand side, the input signals coming from our ADCs are actually quite heavily distorted because these are chirp signals. They should really have a constant envelope with a flat top, but we can see that's not the case. These are really quite distorted, and that's just caused by the analog path that these signals have passed through. So there's not really much we can do about that. We just have to trust and hope that our equalizers are going to be able to correct that distortion. And in fact, we can see on the right-hand side of the slide that these equalizers seem to be doing a pretty good job, because now at the equalizer outputs, we can see that there is a nice flat constant signal envelope across these chirp signals, except in that filter overlap region where we can see that raised cosine response shape in the overlaps exactly like we would expect. So far, this is looking pretty good. So next, of course, all we need to do is add together those three equalized ADC channels, and that effectively gives us the reconstructed chirp signal. So that's the fourth graph on the right here. We can see the sum, which does now have a nice constant envelope across the entire frequency spectrum. So that's a good sign. That's showing us that it's the chirp seems to be reconstructed well. And so finally, all we need to do is compare that reconstructed chirp with the original clean chirp that we transmitted. And so by subtracting one from the other, we can then calculate the error, which is the final graph in the bottom right of the slide there. And so the first comment I can make about this error is a piece of good news, which is that we do not see more distortion in the filter overlap regions of that error signal. And I think that's really important because really this entire frequency interleaving concept is happening in those filter overlap regions. At all other frequencies, we're just allowing the signal to pass through. And it's really in those overlaps where we need to be very careful about getting the gains and phase responses matched perfectly. And so if there was some problem here, we would really expect to see it in those overlap regions, which we do not see. So that's a piece of good news. But the second comment here is a piece of bad news, which is that the overall level of that error is a bit higher than it should be. We investigated that, and we did find that the main cause of that was that we were failing to drive the ADC up to full range. And in fact, our signal was quite heavily attenuated below full range. And so, of course, that was diminishing our SNR. We did try to solve that problem. We inserted an RF amplifier, but unfortunately that RF amplifier turned out to be quite nonlinear, and so that introduced more problems than it solved. And so unfortunately, with time running out in our project, we decided we would just have to calculate mathematically what the error would have been if we could have driven the ADC up to full scale. And so after making that mathematical correction to effectively reduce the error, we were able to get our final result here was that the equivalent number of bits at the output of our frequency interleaved ADC was about 8 bits, or a little bit lower at some frequencies. Now, AMD Xilinx, as far as we know, do not publish any results on the equivalent number of bits in their ADCs. But we did find an academic paper that claimed that they had measured somewhere between about 8.3 bits and 9.3 bits. And so if that claim is true, then we're quite satisfied with this result, because perhaps we're somewhere within 1 bit of the theoretical ideal, and maybe we could optimize our equalizer calculation or our experimental setup to get an extra half a bit or so. But overall, a satisfactory result. So I'd like to finish here with what I think is probably the most important question of all, and that is about the practicality of this frequency interleaving idea. And this really brings us back to that question of how many coefficients do we need in those equalizing filters in order to get sufficient performance, in order to get that distortion down to those levels that we measured. So we investigated this, and we found that, roughly speaking, we need about 80 to 100 coefficients in each of those equalizing filters. And I think in a traditional DSP design, we would look at these numbers and say, okay, no problem, 100 coefficients in a filter is no problem at all. But let's not forget that in this design, we are talking about applying these filters at very high sample rates. So even with an efficient polyphase architecture, we will need to parallelize these filters quite heavily. And the exact numbers here depend on some architectural decisions, but roughly speaking, we're going to need about 2,000 or 2,100 DSP slices in order to implement those filters. And this is not great news, because remember that in our whole device, and quite a large device, we only have about 4,200 DSP slices. And so we're talking about wiping out 50% of all of our DSP slices just to acquire our signals. So that's before we've even really started to do any processing on that signal. But nonetheless, there are still some 2,000 DSP slices remaining afterwards. And so there is quite a lot of potential there to do more processing. And so we do think that there are some practical applications for this frequency interleaving idea. But that's the end of the presentation. So I'll just leave you with a few free resources here. First of all, 2 of our previous webinars overlap very well with today's presentation. First of all, there's SDR, software-defined radio, with RFSoC that has quite a bit of overlap with today's presentation. There's a YouTube link for that there. Then secondly, a more general presentation about how to develop fixed-point digital signal processing components for FPGA and ASIC targets. There's a link for that one there. Then, of course, there's also the video that I mentioned earlier, where I was talking about last year's spectrum monitoring demo. You can see that one there. And finally, of course, if you have any technical questions, then feel free to get in touch. There's my email address there. Or if you're more generally interested in Enclustra's products or services, then you can reach us through the main communication channels. Otherwise, thank you all very much for your time, and I will gladly take your questions. Thank you very much.
Thank you very much, Harry. It was a fantastic presentation. We already have a couple of questions from the audience that maybe if you are available, we can start thinking in answering those questions. Everybody, if you have any further questions, please use the chat. Otherwise, you can also send us an email to webinars@enclustra.com, where we can actually direct these questions to Harry. And Harry, if you will, I have a very first question that it says, since the ADC input was attenuated, did you consider the consequences for auto-calibration? Did you try disabling it?
So this is a great question. The short answer is that we did not have time to take this into account. I know what you're referring to. This is the RFSoC own calibration for its time interleaved ADCs. We have experimented with that with last year's demo, but we did not take that into account with this project. It is possible that that was causing our results to be a little bit worse. We did not try disabling it. We really should have. So that's a great question, and it's very much on our to-do list of what we want to test later this year.
Fantastic. The second one that we have here is, how do you handle channel-to-channel mismatch, such as gain, offset, or timing skew between the different ADCs?
Yeah, so that all comes out in the equalizers. So those are all linear effects, basically. Gain and delay mismatch, those are all linear. So as long as they don't vary as a function of time, so as long as they don't vary after you do your calibration, then the equalizers will fix all of that for you. Of course, if they do vary after you've done calibration, then you would need to either recalibrate or have some kind of adaptive calibration. But basically, the equalizers solve those problems.
Fantastic. The third one, how scalable is this frequency interleaving approach? Could the technique be extended beyond the 3 ADCs?
Yes. So that was one of our big goals here, was to make something that is fully scalable. So this is infinitely scalable in theory. Of course, in practice, we'll hit practical limitations at some point, but the whole concept does work. There's a little bit of design work you need to do to select the ADC rates in all of your channels so that you align those Nyquist zones in an optimal way. That also depends a bit on your anti-aliasing filters that you have on the analog side. But you can prove that this is infinitely scalable. And in fact, it does get easier and easier as the frequencies increase. So yes, it is fully scalable.
Fantastic. And the fourth one, what kind of calibration or compensation is implemented to maintain coherence between the ADCs over time as temperature varies?
Yeah, so this kind of connects back to the previous question. So we did not implement any adaptive or even sort of semi-adaptive calibration. We just had offline calibration for this master's project. We are not sure what kind of update rate would be needed, and that would really dictate how you would do this. We think it's reasonably slow varying, and so some kind of sort of occasional calibration would probably work quite well, but we have not implemented that yet.
Fantastic. Well, we don't have any more time for some questions. If the audience has any more questions, we can always respond to you directly on the webinars at Enclustra.com, where Harry can help us to answer all these questions. In the other hand, as Harry mentioned as well, you have available in Enclustra.com, you have available this presentation if you want to download it. If you have any projects as well, please send us an email to sales@enclustra.com, and we can make sure that our team of engineers, they can set up a meeting with you. And lastly, also please check our different publications and the different presentations that we also have in Enclustra.com, so you can make sure that you can have even more training and more knowledge about this topic and any more topics that we have as well in our publications. So thank you so much, Harry. It was fantastic. Thank you again for being here. You are our expert, and thank you for the time that everybody took to be in this presentation. And again, if you have any questions, please just drop a message to us. Thank you so much, and see you soon.
Introducing the ultra-compact RFSoC module for software-defined radio applications. Imagine a breakthrough that brings unparalleled speed and precision to the most challenging RF applications. Presenting to you the Andromeda XRU50. This innovation offers an impressive array of features, from a remarkable number of built-in digital-to-analog and analog-to-digital converters to minimal crosstalk between RF channels. Comes in the smallest form factor on the market. Powered by AMD Zynq UltraScale Plus RFSoC, this module offers 8 digital-to-analog converters and 8 analog-to-digital converters for direct RF signal sampling and synthesis, with blazing fast CPUs up to 1.3 GHz. Engineered to meet the demands of 5G networking, phased array radar, and satellite communication applications. You can find it in 2 variants. Choose your perfect configuration with our Early Access Program Development Kit. Get started now.